All right, this is going to be our walkthrough for the homework assignment titled Mean Value Theorem for Integrals. And so all we're going to do here is we're just going to find the average value of each of these functions on the interval given. Right? So we're just going to use the mean value theorem formula, which is 1 over b minus a times the integral from a to b of f of x dx. Right? So that's our mean value theorem. So there's not a whole lot going on here that's different than all of our regular integration. We just have to remember to put that coefficient out into the front. So this one should be 1 over 3 minus 1 times the integral from 1 to 3 of 3x squared minus 4x plus 1 dx. Well, that ends up being 1/2 of this integral, which is, using the power rule, x cubed minus 2x squared plus x evaluated from 1 to 3. So we end up with 1/2 well, 3 cubed is 27, minus 2 times 9 is 18, plus 3, and then minus 1 minus 2 plus 1. And so if we go through and do all of the arithmetic on that, right, the 1 minus the 2 plus the 1, that's actually 0. So it's just half of 27 minus 18 plus 3. 27 minus 18 plus 3 is 12. So half of that is 6. All right, for our next one here, it's just going to be 1 over pi over 4 minus 0 times the integral from 0 to pi over 4 of sine x cosine x dx. And so we have two options here. One is to, well, actually there's multiple options. We could do u equals sine x and do a u sub, or u equals cosine x for a u sub. Or we could multiply what's inside of here by 2 and what's outside by 1/2 and rewrite it using a double angle identity. But I think we'll just go ahead and do the simplest substitution, which is let u equal sine x, which means that du is cosine x dx. Now we have to remember to be careful about this, though. When we do our integral, we have to change our limits of integration, right? So when x is 0, right, the sine of 0 is just 0. So that'll stay as 0. But the upper limit's going to end up changing, right? When x is pi over 4, the sine of pi over 4 is root 2 over 2. So our numerator needs to become, or not our numerator, but our upper limit needs to become root 2 over 2. And then we end up with u for the sine x, and then our cosine x dx is just du. So 1 over pi over 4 is just 4 over pi. So we now have 4 over pi times the integral of u, which is u squared over 2, evaluated from 0 to root 2 over 2, which we don't have to worry about switching back into terms of x because we converted our limits. So we now just have 4 over pi times root 2 over 2 squared over 2 minus 0. And root 2 over 2, well, that's just 2 over, if we square it, that's 2 over 4. Right? 2 over 4 is 1/2. And if we take 1/2 of 1/2, that should be 1 over 4. So we have 4 over pi times 1 over 4 minus 0 still. Well, that just ends up being 1 over pi. All right, for our next one here, we're again going to do a substitution, but first let's write it out here. We have 1 over 1 minus -1 times the integral from -1 to 1 of 2x over 1 plus x to the 4th dx. And so I'm going to recognize that this looks similar to an inverse tangent integral that we could do, like if it was 1 over 1 plus x squared. If I rewrote x to the 4th as x squared squared and let u equal x squared, then we'd have 1 plus u squared in the denominator. And the derivative of that x squared would be 2x, which is what's in my numerator, which would be really convenient for a u substitution. So let's let u equal x squared, then du is 2x dx, which we should see gives us 1 over, well, 1 minus -1 is 1/2. So we have 1 over 2 times the integral of du over 1 plus u squared, which now becomes inverse tangent u when we integrate. But before we do that, we need to recognize, of course, that we just need to change our limits of integration, right? -1, when I square -1, right? If x is -1, then when I square it, u is just 1. And then in the denominator, or sorry, in the upper limit, when I take the 1 and square it, that's also 1. And so right here, we don't even actually have to do the integration, right? Because we have a rule that says the integral from a to a, or from 1 to 1 of any function, is just 0. And so we can just say this is equal to 0. Now, if you want to, you could go down here and you could say, okay, this is 1/2 of the inverse tangent of u, evaluated from 1 to 1, which we know is, of course, pi over 4. Well, pi over 4 minus pi over 4 is just 0, and so that's just 0. All right, for our next one here, we'll start it off as 1 over 3 minus 0 times the integral from 0 to 3 of 5x plus 1 to the 1/2 power. And of course, if we wanted to do the substitution here, we wanted to let u equal 5x plus 1, then du would be 5 dx. Well, that would mean that we would need to put a 5 on the inside of this and a 1/5 on the outside of this. And so now we should be able to rewrite this as 1/15 of the integral of u to the 1/2 du. And when x is equal to 0, u is equal to 1. So our lower limit will become 1. And when x is equal to 3, u is equal to 16. So our upper limit will become 16. And now we can do 1/15 of the integral of u to the 1/2. So that's going to go up to be u to the 3/2. And then we'll divide by 3/2 or get 2/3. So we have 2/3 u to the 3/2 from 1 to 16. Well, that's 1/15 of 2/3 of, well, u to the 3/2. So 16 square rooted is 4, and then cubed is 64. And then if we do that with 1, it's just 1. So we end up with 1/15 times 2/3 times 63. Well, 63 divided by 3 is just 21. So we have 2 times 21 over 15. And we could simplify that down. We divide them all by 3. We end up with 2 times 7, which is 14 over 5. All right, for our next one here, we're going to do another u substitution, but we'll start off with 1 over 1 minus -3 times the integral from -3 to 1 of our function 2x plus 3 to the power of 4. And we're going to want to substitute that 2x plus 3 out. So we'll do u is 2x plus 3, and du is 2 dx. So we want to put in a 2, and we'll also want to put in a 1/2. Right? So now this will become a 1 minus -3 is 4. So we're going to have a 1/8 out in front. This is 1/8 of an integral of u to the 4th du. And when x is equal to -3, our lower limit, then u should be equal to -6 plus 3, which is, again, -3. So our lower limit now is still going to be -3. And when x is 1, u should be 5. And so now our integral is going to go from -3 to 5. So we end up with 1/8 of u to the 5th over 5 from -3 to 5. And that will be 1/8 of, well, let's see, u to the 5th over 5. When u is 5, that's really just going to be like 5 to the 5th over 5 to the 1st, or 5 to the 4th. So 5 to the 4th is 625. And then -3, if we raise that, we'll put our minus, and then it's going to be a negative, right? Negative 3 to the 5th power is 243. So that's a negative 243 over the 5. And so if we just do that subtraction, right, 625 times 5, that's 3,125. And if we add to that the 243 and then divide it all by 8, I'm not going to bore you with the arithmetic, but it comes out to be 421 over 5. All right, for our next one here, we're going to integrate tangent. So we got 1 over pi over 3 minus pi over 6 times the integral from pi over 6 to pi over 3 of tangent x dx. Now, we proved in class what the integral of tangent is using a u substitution. So hopefully you've got that memorized. If you have it memorized, we are just going to use it. But remember that you can always write it as sine over cosine, and then you do a u substitution for cosine to integrate this if you don't remember the rule. So pi over 3 minus pi over 6 is just pi over 6. So we have 1 over pi over 6. And we're going to just do the integral, right? The integral is negative natural log absolute value cosine x. And we're going to evaluate that from pi over 6 to pi over 3. And so, if you don't remember that integral, you should. But if you don't, always you can do the u sub, write it as sine over cosine, and u sub out the cosine. So out of the front, 1 over pi over 6 is just 6 over pi. So we've now got 6 over pi times the negative natural log of the absolute value of the cosine of pi over 3. Well, the cosine of pi over 3 is just a half, so we'll put in a half there. And then we will subtract, right, the opposite of the natural log of the cosine of pi over 6. So that just becomes a plus. And then it's the natural log of the cosine of pi over 6, which is root 3 over 2. So we end up with 6 over pi times negative ln 1/2 plus ln of root 3 over 2. And if we use log rules there, it's just like doing ln root 3 over 2 minus ln 1 over half, which means we can put those into a fraction, right? It's 6 over pi, a fraction using one logarithm, the natural log of root 3 over 2 over 1 over 2. Well, the 2's in the denominator should both cancel, and the root 3 over 1 is just root 3. So this is 6 over pi natural log of root 3, which is our final answer. All right, for our next one here, we're just going to start off putting it into our mean value theorem formula here. So we've got 1 over 3 minus 1 times the integral from 1 to 3 of x to the negative 2 minus x. 1 over 3 minus 1 is just a half. And the integral of x to the negative 2, and that goes up to be x to the negative 1, and we divide by negative 1, so that's negative x to the negative 1, or negative 1 over x. And then minus x squared over 2, and we'll evaluate from 1 to 3. So we just end up with 1/2 of negative 1/3 minus 9/2 for when you plug in the 3, and then minus, and then when you plug in the negative 1, it becomes a positive 1 inside of there. Sorry, we're putting in a positive 1. I thought we were putting in a negative 1 for a second. So it's a negative 1 inside there, and then minus 1/2. And so we've got a 1/2 out in front, which we'll deal with in a second. We've got a negative 1/3 and a plus 1 here. So that's going to be 2/3. And then we've got a negative 9/2 minus a negative 1/2. So negative 9/2 plus 1/2 should be negative 8/2. Right? Negative 8/2 is just negative 4. So we've got 2/3 minus 4. 2/3 minus 4 is 2/3 minus 8/3, or sorry, minus 12/3, which is negative 10/3. So we have 1/2 of negative 10/3, which is just negative 5/3. And just a couple more here to go. So for number 8 here, we're just going to have 1 over 2 minus negative 1 times the integral from negative 1 to 2 of e to the 2x dx. And we know that the integral of e to the u is just e to the u, but we have e to the 2x, so let's let u equal 2x, so du will be 2 dx, which means I'll just throw a 2 in here with a 1/2 out in the front to cancel it out. So that means my integral should now become, well, 2 minus negative 1 is 3. So we end up with a 1/6 out in front when we do the 1/2 times the 1/3. And then it's an integral of e to the u du. And, well, the negative 1, so when x is negative 1, u should be negative 2. So we'll change that to a negative 2. Okay? And when x is 2, u should be 4, so we'll change that to a 4. And that gives us 1/6 of the integral of e to the u is just e to the u. And then we have from negative 2 to 4. So we have 1/6 of e to the 4th power minus e to the negative 2 power. And that answer is fine. You can write 1 over e squared there if you want, but I would take that answer. All right, just 2 more to go here. So our second to last one here, we're going to have 1 over 5 minus 2 times the integral from 2 to 5 of x minus 3 to the 6th power. We're going to do a little bit of a u substitution. So we're going to let u equal x minus 3, and du will just be dx. So we end up with 1/3 of an integral of u to the 6th du, and this is where you want to be careful, right? Oftentimes, particularly when there's no switch with the dx and the du, people forget to change their limits of integration, so don't forget to do that, right? When x is 2, u is negative 1, and when x is 5, u is 2. So we should end up now with negative 1 and 2 as our lower and upper limits here. So we have 1/3 of u to the 7th over 7 from negative 1 to 2. So we've now got 1/3 of 2 to the 7th. Well, 2 to the 7th is 128. So we have 128 sevenths minus, and then negative 1 to the 7th is negative 1. So minus negative 1/7. So we have 129 sevenths times 1/3. Well, 129 is divisible by 3, goes in 43 times. So that becomes 43 over 7. All right, and on my last one here, we've got x squared plus 5x plus 6 over x minus 1. So we're going to do 1 over 4 minus 2 times the integral of that function from 2 to 4. But in order to integrate that function, it would be really good if we just divided the x squared plus 5x plus 6 by x minus 1. So I'm going to use synthetic division with a 1 up in the box for the x minus 1, and a 1 for the x squared, a 5 for the 5x, and a 6 there, to see what we get when we actually divide those out. So we bring down the first one, multiply the bottom one by what's in the box, which is 1. We'll add those together, which is going to give us 6, and multiply by that 1 in the box and put it up there. And then we'll add those and get a 12. Right? And so that tells us that x squared plus 5x plus 6 divided by x minus 1 is equivalent to x plus 6, right? 1x plus 6, plus our remainder of 12 divided by x minus 1 dx. And so as we go about doing this, we can just, I think it's going to be useful for us to note that off to the side, if I wanted to integrate 12 over x minus 1, right, I would have to do a u sub for x minus 1 where du would be dx. So we'd end up with the integral of 12 over u du which is 12 natural log absolute value of u, plus your constant, of course, which I don't have room for here, but we'll write plus c anyway. And then it would really just end up being 12 natural log absolute value x minus 1 plus our constant. Well, this is within a definite integral, so we don't need to worry about the plus c, but we can recognize that if we do this work off to the side to see what that integral becomes, then I don't have to split this into two integrals, one where I do a u substitution and one where I don't, because the one where I do the u substitution, I then have to change the limits, and that just kind of becomes a pain. But if I can do it all at once, if I can just do this work over here in my head, or do it off to the side, we can see that this becomes 1/2 of x becomes x squared over 2, 6 becomes 6x, and we get 12 natural log absolute value x minus 1, all evaluated from 2 to 4. And now we should just be able to simplify this down. It's 1/2. When we plug in 4 squared is 16, divided by 2 is 8. So we have 8 plus 24 plus 12 natural log 3. And then minus, when we plug in 2, it's 2 plus 12 plus 12 natural log 1. Well, we know that the natural log of 1 is just 0, so we can get rid of that. So we end up with 1/2 of 8 plus 24 is 32, and then we're going to subtract 2, which is 30, and we're going to subtract another 12, which is 18, plus 12 ln 3, which just gives us 9 plus 6 natural log of 3 as our final answer there. And that is the end of our walkthrough for the mean value theorem for integrals homework assignment.